All right, so this is this week's open source hardware and EDA seminar, and to this week we have Eric Keiter. He's a distinguished member of technical staff at Sandia National Laboratories. You got your PhD from University of Wisconsin, Madison, and looks like you started working on Xyce. You say it's Xyce, right?
Yeah, it's a Z sound at the beginning. Xyce.
Xyce. So he started working on Xyce. He's actually like a physicist. Plasma stuff, and you started working on Xyce in '98 when you went to Sandia, and you're still working on it today. So
yeah, some people never learn.
so yeah, so I'll just summarize your bio that way, and then let you take over.
Okay. Yeah, so let's see if I can find my slides here. Okay, I'm going to try to share them. Thanks for the introduction. So hopefully that's visible. I'm going to now go into presentation mode, so hopefully that'll work. You guys see that?
Yep, looks good here.
Okay. Okay, so yeah, so I've been working on Xyce for a long time, and I'll give you a little bit of a brief history of that name. So I mean, Xyce is a SPICE style simulator, circuit simulator. And almost every SPICE simulator that you ever hear about, you know, it's something SPICE, you know, M SPICE, P SPICE, H SPICE, you know, AIM SPICE, etc. And I guess we just didn't want to follow the crowd too much, and so we had a bunch of meetings where everybody threw out different names. And one guy that I knew had read an article that said that some really high fraction of startups succeeded as long as they had an X in their name. So we decided to come up with a name that sounded kind of like SPICE but had an X in it, and so that's where the name Xyce came from. Anyway, so the talk it's kind of got two parts to it. The title said polynomial chaos methods, and I am going to talk about that in the second half of the talk. The first half of the talk is more just about Xyce in general, so it's kind of first half, general Xyce talk, second half polynomial chaos. Okay. So as I mentioned, Xyce is a SPICE compatible or SPICE style simulator. We started developing it about 20 years ago. It's loosely, the input file is loosely based on what Berkeley SPICE had as an input file. So it's very similar to what might go into H SPICE or P SPICE, etc. But we didn't start it as a branch off of any open source tool or any known simulator like SPICE. We basically wrote it entirely from scratch ourselves. And the reason that we did that was because we kind of had a mandate at the very beginning that they wanted Xyce to be a parallel code. And so we've written it to be distributed memory parallel, which means message passing. So it's MPI based mostly, although there is some threading in it. And we were the group of people that were doing the coding early on, and actually this remained true for a long time, was a group that was in the high performance computing section of Sandia. And there was a very common lore within Sandia, which was that if you wanted to have a code that performed well in parallel, you really had to just design it from scratch to be a parallel code. Like if you just taking an old code like SPICE 3 and hacking it to run in parallel, you could probably get a little bit of speed up out of it, but you really couldn't get great scaling if you did it that way. So that's why we wrote it from scratch ourselves. And the distributed memory aspect of it really required us to have a lot of unique solver algorithms, which I'll talk about a little bit. And also for anybody to bother using the code, we had to support most of the industry standard models. And so we have a Verilog A compiler, which will accept most Verilog A models. Let's see, and so anyway, we developed the code for about 10 years or so. And then around that time, we decided that we really should open source. So we open sourced in 2013. That was with Xyce 6.0. Since then, we've had a whole bunch of releases. Obviously, 2013 was a while ago at this point. And so the most current release is version 7.3, which is coming out really, really soon. Like we have this whole checklist we have to go through for each release. And I think pretty much all the checklist has been checked off at this point. So it might come out today. If not today, maybe tomorrow, something like that. So why did we bother open sourcing? A lot of that was to foster external collaboration. I feel like we get a lot more feedback the more people who use the code. And there's obviously, even though Sandia is a very big lab with like 15,000 employees, there's still a lot more people outside of Sandia than there are inside of Sandia. So I figured if we could get traction externally, we would just get a lot more, a lot more information. Also, just philosophically, we're taxpayer funded, so there has been a fairly high level edict from our government agencies saying that if you can open source your code without breaking the law, you should do that. And we felt that we could open source our code without breaking the law, so we did. And then also, I guess one thing that's happened is that since we've become open source, we've actually attracted new streams of funding. And some of the streams of funding that we're getting are ones that actually require Xyce to be an open source code. So those are all sort of reasons why we did this. So anyway, part of why I'm giving this talk, part of why I'm giving other talks elsewhere is I hope people will use the code and let us know how it goes. Let's see. So just to give a sort of a high level view of Xyce's capabilities, like most Xyce simulators, there's a lot of sort of standard analysis that we support in that, including steady state, DC, transient, frequency domain, small signal, AC, noise, etc. And we also support a lot of post-processing options, dot measures and dot Fourier, things like that. We also support a lot of common output and input files. So it's getting, we hope, easier and easier to have Xyce interoperate with other tools. And also we have a lot of support for expressions and also for Verilog models. So that's another aspect of the code that's important. There's a few things in the code that I think are not so commonly found in, at least in open source tools. Some circuit simulators have the large signal version of frequency domain calculations, which is harmonic balance, but most circuit simulators, especially in the free open source world, don't have harmonic balance, and we do. We've also spent a fair amount of time implementing various UQ methods, including random sampling analysis. A few years ago, I spent a lot of time implementing analytic sensitivities. So there's a pretty powerful sensitivity capability in Xyce. And most recently, I've implemented polynomial chaos methods, which is another way of doing uncertainty quantification. So I'll be talking about that later. Before I get to that, I'm just going to talk a little bit about Xyce's parallel capability just in general. Making circuit simulation work in parallel is kind of difficult, at least if you're a parallel computing person and you're coming from a different domain, where maybe you were solving fluid flow equations or electromagnetic equations or something like that. In some respects, circuit simulation is a bit harder to do well in parallel. And the reason for that is that the matrices that we have to solve for circuit simulation tend to be a little bit more strange. So in fluid flow calculations and finite element calculations and plasma calculations, things like that, you're almost always solving a homogeneous set of differential equations on a mesh. And the discretization that you apply at each mesh cell is basically the same. And so that leads to nice regular patterns and matrices. That is a lot less true in circuits. What you tend to get in circuits is a somewhat heterogeneous structure. You can have some nodes that are connected to thousands of things. You can have other nodes that are connected to hardly anything. You can also get really bad scaling. and I should say, there are, of course, some circuits that have lots of structure, but there's others that don't. And it's really hard to predict ahead of time, what you're going to get. So all of these issues make running, solving these problems in parallel a lot harder. And so that's something that we really focused a lot on. So one thing that we've done in Xyce is we've made it so that it actually does two different parallel partitions. There's the two most expensive aspects of a circuit calculation are, number one, the device evaluation, which is these are the calculations that are performed where you sort of loop over all your device models and you figure out what coefficients have to be plugged into your lens that you're going to solve. So that's one phase, and that can be fairly expensive. And then the other phase that has expense to it is the matrix solve, and that's basically once you've loaded all these values into your matrix system, then you actually want to solve it. And what we found is that the optimal parallel partitioning for these two things basically don't have a whole lot to do with each other. For the device evaluation, there's almost no communication happening, so all you really care about is making sure you get a good load balance. So some devices are very expensive to evaluate. Like if you're evaluating a modern MOSFET bundle that has many thousands of lines of floating point operations. That's fairly expensive, but another device might be a resistor, which basically costs almost nothing. So you want to make sure you've done your load balance right, but you don't have to worry about communication. And so the device evaluation is sort of embarrassingly parallel. On the other hand, on the matrix side of things are a lot more difficult. So that's where we have to really apply a lot of cleverness, or at least we hope it's clever. And so in between these two partitions, there's basically a global reordering and repartitioning. There's essentially a big communication strategy that has to happen between those two. But basically, all the code for that is set up nowadays. So we really can just focus on getting the two partitions to work well. So as far as getting matrix solvers to work correctly for circuits, I guess another detail about all of this is that that I could have mentioned earlier, but I didn't, is that so most SPICE simulators are using what are known as direct methods to solve their matrix, which basically means they're doing something kind of like Gaussian elimination. And that's a method that will give you a fairly precise answer, and they're very robust, but they tend to scale very poorly. I mean, even the most advanced direct methods really start to bog down like crazy once you get up to in the hundreds of thousands of unknowns. So if you're going to go above 100,000 unknowns or so, direct methods don't work so well. On the other hand, iterative methods can scale much better, and they're also a lot easier to set up in parallel because there's not as much communication required. But they also tend to be a lot more fragile, and so a lot of our research in this area has been around how do you apply iterative matrix methods to circuits. And some of what makes that hard is some of the stuff I mentioned earlier, badly scaled DAEs, non-symmetric matrices, strange connectivity, and so on and so forth. So if you try to do something that's basically a standard black box method, where you just sort of download PCE or Trilinos or, I don't know, whatever your favorite solver library is, and then just plug it in, it probably won't work very well. And so, that's sort of what I just described there, where you've downloaded some solver and plugged it in, is kind of represented by this black box here. It says ILUT and GMRes being the iterative solver, ILUT being the preconditioner. That probably won't work if you just plug that in naively and hope for the best. So what we've basically developed over time is that you really have to do sort of a sequence of different operations on the matrix and employ sort of an overall strategy, because there really is no one single preconditioner that'll just do the job for you. And in fact, not only do you have to employ strategies, you often have to imply there's multiple strategies that one might choose to use. And so these two sort of, strategy one and strategy two that I'm showing here on the slide, these are both from actually a fairly old paper at this point, a paper from about 10 years ago that we presented, where we basically compared these two strategies. The second strategy represented what felt like at the time to be a pretty good breakthrough on getting circuits to work in parallel. So I'll talk about that a little bit now. So you notice both of these have this thing that I call a singleton filter at the beginning. And what that does is, if you're familiar with circuits, especially digital circuits, you know that most circuits have lots of things connected to them. And some of those things are connected to many things. Like, for example, a power node is often going to be connected to a really, really large number of transistors in the circuit, either directly or indirectly. And that's what this histogram is showing. Other things like buses and clocks, they won't be connected to quite as much as a power node, but they'll be connected to lots of things. And then there's other types of things that are connected to less and less and less. Most nodes in the circuit aren't connected to very many things. Most of your circuit matrix is fairly sparse, but here and there you've got these very dense objects or very dense things. So it behooves you to get rid of those if you can. And so that's what we do. We basically employ both a matrix pre-process and post-process, where essentially we treat these like boundary conditions. We already know what the value of the power node is, so we don't have to solve for it. So basically, we factor all of those out of the system before we even hand it over to the solver. So that's the first thing we do. Another thing that we sometimes do, not always, but it was the focus of that paper from 10 years ago, is to employ what's known as a block triangular form. And that's a form that you can basically discover in a matrix if you apply a reordering routine called Demolge-Mendelssohn. And we discovered a long time ago that an awful lot of circuits that we had seemed to have this form, somewhere inside the matrix. So, or we were able to basically expose this form if we applied that reordering routine. And if that reordering routine did produce a form like this is really advantageous. And so what you wind up here is this. It's an upper triangular, but these blue dots are all blocks. They're not individual nodes of the matrix. And so if you can get your matrix into this form, it's really, really advantageous, both for serial direct and for iterative solvers. So that was phase 2 of this particular strategy that I'm talking about. And then after that, once we have that block form, we apply graph partitioning, and we found the hypergraph was very advantageous here. It was, for at least a number of circuits, we saw a significant reduction in communication volume if we use hypergraph, so we typically do that. And then once we have it in that form, then actually with this particular combination of pre-processing steps, then the Bloch-Jacobi preconditioner works pretty well, and then GMRes is the final bit. And so, so for a couple of circuits back around the time of the paper, we saw a really, really good performance. And so you can see here sort of the progression of the matrix through different through different processing steps. The bottom 2 pictures are basically showing what the matrix looks like, either on 4 processors or 8 processors once we've done the BTF plus hypergraph partitioning. And you can sort of tell just by looking at these, this looks like it's going to perform pretty well in parallel. Almost all of the information in the matrix is contained within those blocks near the diagonal. And in our experience, it did work really well. For a lot of these circuits, we got really great speed up. The strategy 1 that I showed in the first slide, which was sort of essentially what happens when you apply a PDE preconditioner to a circuit. That circuit had a lot of trouble. It took 500 GMRes iterations to solve, and basically took 5 minutes or so. But using this BTF approach, it basically took like 1/10 of a second. So pretty significant improvement. And basically, the first method didn't converge at all. So we really thought we'd done something really cool here. We really thought, okay, this is cool. We can solve circuits now. But it turned out that wasn't always true. So what happened in the years following was that occasionally we would be given a circuit by Sandia designers that really didn't work with the BTF structure. And we've done a little bit of looking into why some circuits have BTF structure and why some don't. I mean, basically, it depends on if the circuit has a sort of a unidirectional flavor to it. If the matrix has a certain asymmetry to it, then BTF really works well. But that's not true for a lot of circuits. Especially, one thing that happened was once process nodes got past about 45 nanometer, we stopped seeing the BTF structure so much. And the reason for that was that I think around 45 nanometer, they started using metal gates and they started using more exotic oxides. And because of that, the oxide models that were in a lot of compact models became a bit more complex. And so that actually completely changed the structure of the resulting matrices. So anyway, this was an example of a matrix or a circuit that failed. This is a fairly large, almost 500,000 or over 500,000 devices, about 500,000 unknowns. And BTF just completely failed. When you apply BTF to it, the matrix really didn't change a whole lot. You got stuck with this really large irreducible block. And so that style of preconditioner really wasn't going to work very well. So this led to the development of a new sort of hybrid solver that we use in Xyce. And I'll explain what I mean by hybrid in a minute, but the hybrid solver gave a much better result. And so the result of the reordering from the hybrid solver is what you see here in this particular, in the final picture here. So what was the deal with the hybrid solver? So the name of the solver, we didn't actually write it. It was actually written by a different group at Sandia. It's called Shilu. And it's basically a sparse linear solve. Yes.
Can I ask you a question back on that design? You said it's a Sandia ASIC. Is it just like,
yeah,
what is it like doing Spice on the full design, or what is?
So in this case, we're running Spice on the whole thing.
So like Spice of a digital circuit, or?
I think this is a mixed signal circuit. It had both analog and digital aspects to it. I mean, I will say, a lot of time the design flow that people typically use for circuits this big doesn't include Spice, or it doesn't include it much, right? You're mostly just simulating standard cells or something like that, and then calibrating timing simulators. We had a few use cases where people really wanted to run, Xyce or Spice on a full design, and that
Mhm.
had to do with radiation effects, and the approximations that a lot of digital tools made didn't really make it very easy to look at certain radiation effects. So that was the rationale for why we were doing that.
Okay.
So I wouldn't say that we don't run 500,000 device circuits every day, uh, but that is one of the targets of our work. So anyway, so getting into what's a hybrid, and I should mention that by the standards of HPC, high performance computing people, a problem that has 500,000 unknowns doesn't sound very big to them. It sounds really big to me, but people that work in like fluid flows, I know people that are often on large supercomputers solving problems that have 10 billion unknowns, something like that. so so from their point of view, what we're doing with Xyce is kind of small potatoes, but we like it. It was still pretty hard for us to do it. So I mentioned this hybrid solver. Basically, we're using a code called Shilu. Shilu's a linear solver framework that's based on Schur complements. And basically, what you do with a Schur complement is you can partition your matrix into this 2x2 sort of structure, or more than that, and then you can recover and then you can basically solve the different parts of it separately. And so you've partitioned the matrix into different pieces, and then this is a hybrid solver in the sense that some of these pieces are solved using direct methods, and some of them are solved using iterative methods, and the coupling is solved with the direct method between the different pieces. The other way in which this is a hybrid solver is that it's incorporating both coarse-grained parallelism, which is the message passing style parallelism we've always done, and it also does fine scale multi-threaded parallelism. So for that circuit that I just mentioned a couple slides back, that circuit, which failed using the BTF preconditioner, actually runs okay. It runs reasonably well with this preconditioner. So we're with the Shilu preconditioner. So this was so this particular, actually this is a slightly different version of the same. It's from the same family of circuits, but it's a slightly different circuit. But basically, it's a 2x2 ASIC, and so it's got 4 tiles that are very similar. The total number of devices is 1.6 million, so there's around 2 million unknowns for this particular study. And we actually were able to run this with our direct solver, KLU, but that's not advisable. When we ran it with KLU, it took around 2 weeks, which most people wouldn't put up with. But with the Shilu solver, we were actually able to get the runtime down to about a day, which is still, it's a pretty slow simulation, but it's still, a day is something you can live with, whereas 2 weeks you might not be able to live with that. So the plot on the right here is showing a scaling study, the speed up versus KLU, which is the 2-week simulation. And the x-axis is the number of cores, and the different lines represent basically different ratios between essentially threading and message passing. So in some cases you might, I guess, like in the most extreme example, you might have 16 nodes and you're only using one, and each, or what am I trying to say? Well, each node is going to have multiple processors or multiple cores on each node. And in the most extreme example, you might only use one of the cores on each node to try and really, if you think your message passing parallelism works better than threading. On the other hand, you might not be allowed to do that because lots of people are trying to use your system. So then you might just want to use all the cores that are present on one node, in which case it's mostly threading. So we got sort of similar patterns. All of them sort of rolled off around 128 cores. So that's kind of where this 1 day number comes from, is around 128 cores. So that was a pretty good success. And this is a method we've applied to a lot of circuits, so we're pretty happy with it. Yes. So that's kind of all I'm going to say about that. I actually meant for this talk to mostly be about other things, but I thought I'd say a few things about that. So I'm going to take a total left turn here. And the reason I'm going to talk about something called polynomial chaos expansion methods in Xyce. So these are methods that I had a research project that ended fairly recently on this topic, so it's kind of on my mind, and so that's part of why I'm talking about it. So the idea behind this is to come up with better ways of doing uncertainty quantification, and the idea here is, in a lot of times you have a circuit or you have some physical problem where you're modeling it with parametric, and your models have parametric inputs. But those parameters, after you've calibrated them, you notice that there's some variation. If you calibrate 100 of these devices, the parameters aren't 100% the same every time. There's a Gaussian, there's some kind of statistical variation associated with that variation, and it might be that might be due to process variations, or it might be due to experimental uncertainties. Maybe your measurements aren't very precise, depending on what type of experiment you're looking at. Just depends. But whatever those variations are, it's often going to be of interest to know how do these variations affect the output of a circuit. And so, so here's a really simple example: CMOS inverter. You're varying the threshold voltage of the two MOSFETs, and that leads to some variation in the output. Slightly different timings on the signals here. So that's a type of problem that's of interest. I mean, lots of people do corner studies, things like that. So that's something that people often want to study if they can. So the obvious solution to this, and this is what lots of people do, is just to do sampling. And there's the idea behind that is just you run the circuit in your simulator a large number of times, and each time you run it, you change your parameter values a little bit, based on some distribution function. And so that should lead to slightly different outputs, slightly different results. And once you've done all your calculations, you can then build ensemble averages or compute moments of the sample outputs. And so you can get things like mean and standard deviation and kurtosis and things like that. You can also look at the tail of the distribution if you're interested in that. And there are lots of types of sampling. There's Monte Carlo, there's Latin hypercube, there's importance sampling, but they're all sort of the same idea in a sense. You're basically changing parameter values, and you're running your simulator many, many times. And that's that's pretty easy to understand. And if you have a mature simulator, that's a nice way to go. But one drawback to it is that it's computationally expensive. And so for a lot of reasons, you might want to avoid it. I will say one thing with Xyce, since we're a free code, we're open source. If you have a really large computer, you can run Xyce as many times as you want. You could launch 100 Xyce calculations or 1,000 Xyce calculations, as long as you have enough processing power. My understanding is that most commercial tools will license. Basically, their licensing won't permit you to do that unless you're willing to pay for 100 licenses or whatever. So for most people, there's some limitations to how much sampling they can do. If you're at a really big company, they can probably afford as many licenses as they want. But if you're at a small company, that's another matter. Anyway, so here's an example. One of our collaborators at USC, they designed a SAR ADC circuit, and we ran it in Xyce and did a corner study. This is 400 corners, I think. And so I think on one of the large computers here, I was running 100 corners at a time, but obviously that's a fairly time-consuming calculation. What can we do to avoid doing this? So the alternate idea is to come up with some kind of analysis method that doesn't involve sampling, where you don't run the circuit many, many times. You instead run a single analysis once, and then somehow compute statistics directly from that output. And so the idea is to represent the random system in a way that would allow us to convert a stochastic system into a different system that doesn't have randomness in it, and then represent the statistics of the stochastic system in terms of the output of this new system. And the idea, and this is not an idea I came up with, this has been out there in the literature for a while, but there's this idea of polynomial chaos expansion methods. And a lot of people have published on this. One guy who's published a lot is this guy from, I think he's at Princeton. And this is a book that's a really important book on this topic. Anyway, the idea behind this is you don't simulate the circuit thousands of times. Instead, you represent uncertain quantities as a finite sum of orthogonal polynomials. And that's what this little equation is showing here. And here, O is a scalar objective function, P is a vector of uncertain parameters, psi is a set of orthogonal polynomials, and there's a lot of different polynomials you could choose, but a very popular one is Hermite polynomials. And then alpha are the scalar coefficients that you use to evaluate the expansion. And there's a lot of mathematical analysis behind this, why this is an okay thing to do. Generally, at least for a lot of problems of interest, these expansions converge fairly quickly. So it's justified to truncate the expansion based on this theorem here. Oh, and I'll also mention that what choice of polynomials you choose depends a lot on what the distribution of the input is. So different polynomials tend to be most appropriate for different types of inputs. So if you have Gaussian inputs, you're probably going to use Hermite polynomials. If you have uniform inputs, you're probably going to use Legendre polynomials. And there's also polynomials that can be used for discrete distributions. I haven't really done that yet, but that's also an option. I guess I'll also mention that the generalized form of polynomial chaos, which this guy Zhu published back in the mid 2000s, the generalized form of it allows you to mix and match these. So you can have parameters that, you could have one parameter that's uniform, another parameter that's Gaussian, another parameter that's, has a gamma distribution, whatever. And the generalized form allows you to mix and match. And all of the advantages of orthogonality still hold up if you do it the right way. So this type of method can be applied intrusively or completely non-intrusively or sort of in between. And we've actually implemented kind of a whole continuum of these methods in Xyce the last few years. In the non-intrusive case, which is what I have on the left side of my continuum here, the non-intrusive case doesn't really require you to change your simulator very much at all. It's a lot like, if you're doing the non-intrusive form of PCE, you're doing something that's a lot like sampling, except that maybe you've changed how you've chosen your sampling points. Like if you're using a quadrature-based method, you're going to want to use quadrature points instead of Latin hypercube sampling points. And then you're basically just doing a fancier post-processing to compute what the coefficients of the expansion are. And so that's very convenient. It is subject to some interpolation error and integration error, but it's pretty easy to set up. And so if you look through the literature, you'll see a lot of names for this. There's stochastic collocation. Another term for that is non-intrusive spectral projection. Both of those are methods where you're basically using Gaussian quadrature to solve for the coefficients. You can also use regression methods in this case, and regression methods are pretty convenient because they don't care as much about exactly which sample points you've used. So you could actually do a Latin hypercube sampling of your simulation, and then use your Latin hypercube sampling points to compute PCE coefficients using a regression method. And so that's one thing I've done. So that's one approach. On the other end, the fully intrusive approach is one where you take this expansion method and you basically propagate it all the way through your system of equations. So every term in the differential algebraic equation system is now expanded using that same PCE expansion. And so that means that every voltage node in your circuit is expanded, every current is expanded, your Jacobian matrix gets expanded, et cetera. And so as you can imagine, setting this up is a lot harder. You basically have to rewrite a big chunk of you have to have some kind of way of taking your original DAE system and transforming it. So you have to have a new layer in your simulator that'll do that. And then once you've done that, you wind up having a new block matrix system that is has its own challenges for solving, right? So the implementation is kind of challenging. On the other hand, there's at least some analysis out there that says the accuracy is more optimal. The residue is orthogonal to the linear space that's spanned by the polynomials. So there's some reason to believe that this can be a more accurate way to go. So those are the two extremes. There's the non-intrusive and there's the fully intrusive. There's also methods that kind of sit in between that I'm just calling partially intrusive here. I would say in spirit, they're a lot closer to the non-intrusive methods, except that in the non-intrusive methods that I was describing a minute ago, that are kind of like sampling. In these non-intrusive methods, you're basically applying your sampling loop as an outer loop around your simulator. So you just run your simulator, over and over and over again in exactly the same way you would have before. In this partially intrusive approach, what I've done this in Xyce is I've basically taken the parametric loop where you might apply quadrature points or Latin hypercube sampling points, and I put that loop at the innermost part of the simulator rather than the outermost part of the simulator. And so essentially, I'm still solving the same set of DAE differential equations. I haven't modified what they are, but I'm solving a whole bunch of them all at once. And I'm essentially doing simultaneous propagation. So from the point of view of the time integrator, I suddenly, or from the point of view of the solvers, I suddenly have a much larger system, but it's a decoupled system. And so each individual sample point doesn't really need to communicate with any other sample point, but they're all sort of sharing the same solver techniques, and they're also sharing the same time stepping. And then at each time step, if you want to, you can then apply one of these non-intrusive methods to whatever output you're interested in. So you can do, you can do a quadrature-based method, or you can do a regression method and get your coefficients. I actually find this middle option to be kind of the most useful in a way. At least if I'm looking at a transient result and I really want to see how the uncertainty is evolving with time. You can do that with pretty easily with the partially intrusive approach. It's kind of tricky to do that with the non-intrusive approach because you kind of have to wait for each one to finish and then interpolate the results. So here you don't have to do any interpolation, so that issue's gone. There's one method in the literature is sort of like that basically is in this category that's called stochastic testing. I believe stochastic testing is basically a regression method that's being applied semi-intrusively. So let's see. So to get into a little more detail here, well, just a little more. We implemented three types of PCE in Xyce, and then we applied them in each of these sort of columns here. So the stochastic collocation, or the non-intrusive spectral projection, that basically evaluates the coefficients using a Galerkin projection, and that basically means solving a formula like this. And so you have to solve this integral here, and typically people use quadrature methods to solve that integral. So to solve that integral using a quadrature method, you need to have sample values at a set of prescribed quadrature points, and so that's what we do. And so if I'm doing this completely non-intrusively, then essentially I'm doing sampling, but the sample points are quadrature points. I mentioned earlier regression PCE. That's also an approach one can take. There's many regression algorithms out there. I'm sure a lot of this audience has heard of them. But the particular version that I implemented for now is least squares regression. But there's a lot of other methods out there, of course. And then also we did actually manage to implement the fully intrusive form over here on the right. That took a lot of work. But it was interesting, so we did. Let's see. To the best of my knowledge, I think Xyce is the only simulator out there that has these methods in it. I could be wrong about that, but I'm not aware of any others. So that's kind of cool. So I'll just talk a tiny little bit more about the fully intrusive PCE. That took a lot of work on our part, but basically what you're doing is you're applying these projections to every part of the DAE. And that means that every vector of the system of equations, your residual vector and your solution vector and so on and so forth, all have to get processed in this way. And then circuit solvers they're solving nonlinear systems of equations, so they always use Newton's method to minimize your residual vector. And so that means that you have to set up a Jacobian matrix, which is the derivative of your residual with respect to your solution vectors. And you can actually construct that. I didn't know how to do this beforehand, but I do now. And you can construct that using a formula that's shown here. And there's a bit of an approximation here at the end. But basically, if you have your original matrix entry, which is df/dx, then you apply your standard projection to df/dx, and then that gives you this term ak, which you can then plug into this formula here. And then these psi's are all basically inner products of different components of the orthogonal expansion. So it is possible to get, if you have a simulator that already populates your original DAE, you can basically apply all of these projections to the different terms of the DAE and to the matrix and get a fully intrusive form of the matrix you need to solve. I'll also mention, if you're familiar with circuit simulation, there's a technique that almost all circuit simulators have to use called voltage limiting. That was something that didn't that most of the PCE literature doesn't think about this because they're not applying it to circuits. But the voltage limiter is basically an additional vector that goes into your system of equations. And not surprisingly, you have to apply the PCE projection to that vector as well. So that's another detail. So the fully intrusive PCE system that you get, there's kind of two ways you can do it. But basically, one way you can do it is this: if you start with your original circuit matrix structure, then basically each node of that circuit then can be exploded into a block which contains all of the PCE terms. And so if your number of quadrature points is P and your number of circuit unknowns is N, then the fully intrusive circuit matrix that you get will then be N times P in terms of size. And you can actually do two different orderings. You can either do the ordering that I'm describing here, where the resulting block matrix the blocks have the same sort of sparsity pattern that the original circuit matrix had. That's one way to do it. Or you can invert it, and you can basically have the block form look like the PCE expansion structure, and then inside of each block you have something that looks like the original circuit matrix. And so if you do that inverted sort of ordering, then you get a structure that looks like this thing in this spy plot in the lower left hand corner here. So PCE tends to give these sort of interesting structures, which you have to do lots of clever things to solve. Let's see. In contrast, I also mentioned the sort of semi-intrusive methods. When we do that, we also get block systems, but they're nowhere near as complicated. Basically, when we do those, the blocks are not the different quadrature points or the different sample points are not coupled to each other at all. And you can order these in two different ways. You can either order it as an n by p or by a p by n. If you do it by p by n, then you wind up with this sort of block diagonal structure, and the basically each block represents a sample point, and then inside of each block you just have the structure of the original circuit matrix. So solving this one is basically just like solving a whole bunch of these separately. There's no coupling between the blocks. The other way that you could do it is to invert the ordering and do n by p. And in this case, the block structure looks like the original circuit matrix, but then inside of each block, you just wind up having a purely diagonal. And there's actually a lot of, we have a solver that actually that can exploit this kind of structure, and it's called Basker. And basically because all of these are basically identical, or a lot of these have sort of identical things in them, you're able to really take advantage of threading in terms of your solve. So I'm really looking forward to doing a lot of research on that, although we haven't had time to do much with that yet. I'm mostly just going to be showing examples with sort of toy problems, but the toy problems are still illustrative. So this is a really simple CMOS inverter, 5 stages. In this case, there's 2 variable input parameters. I think they're both threshold voltages, although I didn't write it down here. Or no, I did write it down. It says 2 threshold voltages. And so basically there's one NMOS model and there's one PMOS model, and each of them have a random distribution on the threshold voltage. And so what I've done here is I've ran the code. I've run Xyce with 1,000 Latin hypercube samples. It's probably overkill. And in the result here, you're just seeing one of the transitions between high and low on one of the outputs. And the gray lines represent all of those samples. I think I must have given it a pretty big standard deviation on the input. I don't remember what I did, but it looks like it must have been pretty big. But that makes it easier to see what's going on. And then from the samples, I computed both the mean and then the mean plus or minus sigma. And then I also did this calculation using one of the semi-intrusive quadrature-based PCE method. And what you see here is that the mean and the mean plus standard deviation from the sampling and also from the PCE method basically lie right on top of each other. So that was nice to see. I mean, this is a small enough problem that running 1,000 samples doesn't take very long, and you probably don't need 1,000 samples anyway. But it was still. I did the 1,000 samples just to really be sure that I'd gotten good statistics, and to be sure that I could trust the resulting mean and standard deviation as sort of a gold standard.
Eric, can I ask you On
Yeah,
that, the minus side of that, the red at the bottom, why does
yeah.
it hit the 0 volts? So like at such an early time when all the random samples don't. Do you know what I
You
mean?
know,
What's going on there?
that's a really good question, and I don't know the answer to that. All I can say is both the Latin hypercube statistics and the PCE did that. Um,
Yeah,
so they both did it. I don't know why the gray lines don't seem to go there, though. That seems a little
yeah.
strange to me. I agree. That looks a little weird. Maybe I
Huh.
shouldn't have shown this example. So, but
Did you do a static noise margin analysis of SRAM cells?
uh, well, one could. I don't think I've done that particular use case for
If
this yet.
if not, we will. So
Oh, okay, cool. Um, anyway, yeah, that would be a good thing to look at. Um, so moving on to another example, this example is very similar. I mean, the previous one was a chain of inverters. This is a chain of inverters that have been where the end has been connected to the beginning, so you have a ring oscillator. And and so in this case, I think so. So ring oscillators can get pretty far out of phase if you tweak their input well, very much. So I was pretty conservative in how much I'm changing the input on this one. I just have a single parameter that's varying. It's also a threshold voltage on one of the transistors. But what you can see here is that and in this case, I guess I'm not showing all 100 samples, but I could have done that. But in this case, as you're seeing here with the 100 samples and with my PCE calculation, everything's lining up pretty well. The mean and the plus or minus, and I didn't do the plus or minus, but the mean and then also the standard deviation, they're right on top of each other again. So, and I guess I'll mention, I'm showing the number of quadrature points here. If I'm doing a fifth order polynomial and I'm just doing a single parameter, then you only need 6 quadrature points. Back here on this one, I was doing a fourth order polynomial and I had 2 input parameters, and that led to the PCE method requiring 25 quadrature points. Eventually, as you might imagine, when you get to more and more parameters, then the number of quadrature points you need can explode if you're not careful. And there's a whole sort of, there's actually a whole field of study known as sparse grids and compressive sensing that you can apply to this type of problem. And when you do that, you can really mitigate the number of quadrature points that you need, because then you wind up doing sort of a hierarchical quadrature calculation. So this picture here, it's another kind of toy problem, but it's one that has a few more inputs to it. This is a Gilbert cell mixer. And for this one, I think there's 8 transistors in the circuit, and I gave all of them a random distribution. So there's 8 random inputs. And then I also did 1,000 Latin hypercube samples, as well as all of the different methods. And so I did the non-intrusive or semi-intrusive spectral projection quadrature-based method. I also did regression PCE, where I'm using a least squares regression to compute the coefficients. And then also I did the fully intrusive PCE, and the fully intrusive PCE and the semi-intrusive spectral projection method. They're both using the same quadrature rules and everything. So they both required the same number of quadrature points. They both required 129. For a regression a regression method, there's really no strict requirement on how many points you use, since you're not using a quadrature rule. It'll just take whatever points you feed the algorithm. I had read somewhere that that to get good results on a regression method, you should oversample by the number of terms you have. And so in this case, I think I forget what order I used, but it's order 2. Okay, it's order 2, and so the number of terms in the expansion was 45 with these 8 parameters. So because it was 45, I chose to use 90 sample points for the regression PCE method. And so then what you see here in this case is that the gray lines are all of the individual samples from the Latin hypercube calculation, and then the solid lines, which basically all lie on top of each other, are the mean and plus or minus 2 sigma from all the different methods, including sampling as well as the 3 different PCE methods. And as you can see here, they line up really, really well, at least to the eyeball norm. They seem to be giving roughly the same answer. And so I also compared these in terms of runtime versus just running the calculation once. How much more time did it take to do these various calculations? So in the case of Latin hypersampling, since I did 1,000 samples, naturally you'd expect the runtime to be on the order of 1,000 times longer. And there's a little bit of overhead in terms of setting that up. And so the scaled runtime for that was slightly more than 1,000x. For the two semi-intrusive PCE methods, NISP and regression PCE, the runtime was consistent with the number of points that I was using. So, NISP required 129 quadrature points, and that took around 126 times the runtime. And then in the case of regression, since I was using 90, Xyce took around a little over 94x. The fully intrusive PCE was not as positive of a story here. That's not too surprising. I haven't really optimized the solvers yet, but if you're trying to solve systems that look like, if I go back, if you're trying to solve matrices that look like this blue thing here, there's a lot more work to be done. So there are a lot of clever ideas out there for how to solve these systems efficiently. And I only just barely got the method working in Xyce by the end of the project. So I haven't really optimized the solvers for the intrusive PCE method yet. But my guess is that even once that happens, they're not going to make up the difference here. And so at least my thinking is that, these sort of semi-intrusive methods are probably the best combination. You're basically solving the same system of equations, and you're just applying a little extra processing to them. So that's kind of the punchline of where this project got to so far. I guess I'll also mention that, I mentioned that Xyce 7.3 is coming out really soon. And 7.3 will actually be the first release where all these methods are officially supported. They've been in the source code for a couple years, but we haven't been able to, for a variety of reasons, we haven't been able to support them officially until now. It mostly has to do with the fact that within Sandia, we're required to support all of the sort of corporate computers, including up until very recently, some that were running a really, really old version of Red Hat Linux. And that really, really old version of Red Hat Linux, the default compilers that were installed didn't support C++11 or C++14. And a lot of the code I wrote for this depended on those more modern implementations of C++. So fortunately, Sandia finally dropped support for those older versions of Linux, which removed that restriction from us. So now that means that in 7.3, which I think is coming out either this week or next, well, very soon anyway, it'll include all this stuff. I guess I'll also mention that if you want to use this stuff, I mean, it's, if you already have a netlist, like for this Gilbert cell, the stuff that you have to add to it to enable these methods is not very much. You just add some commands like what you see here in the lower left-hand corner. And you don't have to do it this way. You can also use, like most Spice tools support things like agauss and aunif for applying distributions to parameters. And Xyce supports all that as well. So the PCE methods are all connected to those keywords in the expression library. So if you wanted to, if you have something that has, if you're accustomed to using those sort of random operators in expressions, you can use that. So anyway, if anyone's interested in using Xyce, I'd encourage them to do it. You can either get binaries. For binaries, you're only going to get like specific code releases, or you can build it yourself. We're pretty happy about the fact that Xyce is now up on GitHub. We've also been spending a lot of time trying to make it a lot easier to build. So that should we've switched over to CMake from the auto tools. So that may seem like a small thing, but it actually, I think, makes a pretty big difference. So and then I'll also mention there's a lot of people that work on Xyce. It's not just me. And and I think that's all I've got for today. So I'd be happy to talk to anybody.
Yeah, I will say I rebuilt it like a couple of weeks back after like a year, and you guys definitely made improvements there. So
okay, good. Glad.
And I also asked a question that you guys answered in like 5 minutes. So
yeah. There's one guy in particular who's pretty good at answering things fast.
Yeah.
So that's good. Yeah, I mean, basically, I mean, we want people to use it, and I think our goal is to get it to a point where it's essentially installable, kind of like what you get with package installers, where you would just say, port installs Xyce, or
Mhm.
things like that. So you wouldn't have to wrestle with this. Our biggest hurdle is that we're sort of married to this solver library called Trilinos,
Mhm.
and Trilinos is this huge library that has a lot of options, and right now, at least, Trilinos has to be compiled with a very specific set of options for Xyce to compile properly, and that's what makes it
Yeah.
hard. um,
Yeah.
but the nice thing is, I mean, Trilinos uses CMake, and we've switched recently to have Xyce use CMake. So I think it's possible to have the two CMakes talk to each other and just sort of make all of it automatic. So that should help. So I'd be happy to answer questions if anybody has any, or not.
Yeah.
So,
No, I'll just comment that I'm excited about this just for memory simulation. I've mentioned it for a long time and have never spent the time digging into it, but
yeah.
Gspice has been our bottleneck now for characterization.
Ah.
Even with the parallel models evaluation. So like
Hmm.
they use Open MP or whatever.
Oh, sure. Yeah. Yeah.
Yeah, but the matrix stuff is then the bottleneck. So
Yeah. I mean, generally, I didn't get into this earlier in the talk, but um, if the cert, so the cost of the device evaluation versus the cost of the matrix solve, those two things scale very differently. So if you're
mhm.
running a circuit that has, 100 devices in it, almost the entire cost is in the device evaluation, and the matrix solve is trivial, almost does
Mhm.
nothing. But as you get bigger and bigger, the device evaluation cost usually scales linearly, and the matrix solve cost scales superlinearly. And so at a certain point, the matrix solve starts to dominate. And then once you start getting into really big circuits, 100,000 or a million or whatever, um, at a certain point, there's a crossover where the matrix just dominates, and
Yeah.
the device evaluation is just kind of in the noise. So
Actually, kind of a random question. You mentioned the singleton kind of
yeah,
pre-filter. What about like if like in particular with memories, if you're like trying to measure something and there's lots of extraneous stuff that you're not measuring, you could almost specify parts of the circuit as not needed to the simulator. And
yes,
um,
yes, you're right about that.
or just a
So
way of like automatically kind of telling the user, these might be things that you don't need.
yeah, so that's a direction that we've intended to go in for a while, and we're actually kind of being paid to look into this at this
Mm.
point. Um, but if you've heard of simulator, if you've heard of these quote unquote fast spice simulators,
Mhm.
um, years ago there was a tool called HSim, I think. It was probably bought by Synopsys or Cadence or whatever, but there's a number of simulators out there that are in this category of fast spice, and they're really targeted at things like memory circuits where you have a lot of very similar or repeating cells, or repeating memory cells. And those simulators are pretty clever at figuring out what parts of the circuit are basically off or basically not changing, and then only simulating the parts that are actually doing something. Um, and they also do other things. I mean, I think behind the scenes they're applying lots of table model approximations, so you don't have to
Yeah.
reevaluate the devices and things like that.
Okay. That's what I
And
thought they were doing. Is just like, yeah,
yeah,
linearizing models and stuff like that.
yeah, they linearize models, and they exploit hierarchy if there is a hierarchy to exploit. So those methods work really well on memory style circuits. I think at least that's what I've always heard. Um, and the more you head in a more analog direction, the more those methods break. Is my
Mhm.
understanding. Um, but yeah, I mean, basically, we should probably be doing more of that stuff in Xyce. Really early in the project, there was a lot of resistance to doing that from our management, uh, because you're not solving all the equations,
Mhm.
and we work in an environment where there's a lot of physics people, and we have a lot of requirements in terms of proving that we actually got an answer that we can reproduce. Um, And so there was a fair amount of resistance to that, but I think that's relaxed a bit. And so so I'm planning to look into that more. I wish we'd made more progress on it than we have so far, but that's part of the plan. So.
Any questions from students? You can raise your hand and I'll give you a voice to talk, or you can type a question if you have any.
So I have a question. So while the students might be, so what do you use, floats or doubles on for the computations? And have you been looking and trying to use the new AI kind of thing that they are like more reduced precision, but they allow you to have a much more throughput on the matrix multiplications?
Yeah, well, mostly we're using doubles to give the short answer. We do have a project that I didn't get into now because I've mostly been a cheerleader for it and I don't entirely understand all of it yet. But we do have a project going on for attempting to use various AI methods to model subcircuits and also complex models. And so for that project, we're invoking libraries like TensorFlow and PyTorch and things like that. And I think some of those libraries are using reduced precision, or some versions of those libraries are anyway. And so there's actually an API for plugging Python-based models into Xyce that came online really recently. And so, if you have a model of a circuit block that's been, that you've constructed using a neural net or something like that, you can invoke it that way. So in theory, one could have a model there that's using reduced precision. There's nothing to stop you from doing that. That hasn't really been our focus, though.
Super interesting talk. I had a similar question maybe about Jose, trying to suss out the performance scaling and scalability challenges. I think you mentioned that as you get larger problem sizes, the matrix solving became kind of the dominant component. Right. Is that primarily communication bottlenecks? Is that bandwidth? Is that latency? Is that synchronization, load balance, or what kind of or is that a trilineous problem?
Well, you'll see. I mean, you'll see that kind of pattern even in serial. If you're using a serial direct solver or a serial iterative solver and not worrying about parallel at all, you'll still see that the matrix solve scales super linearly.
But if you wanted to go really big weak scaling, what prevents you from getting good weak scaling linear speedups? Is that communication or?
Well, if you're talking about, let's see. So if you're talking about weak scaling, I mean, eventually just each processor just doesn't have enough to do. So it's one thing that can happen. So if your problem size is fixed and you keep throwing more and more cores at it, eventually, you're just not utilizing the cores very well.
So with weak scaling, we'd be adding more work.
Sorry, misunderstood. So with weak scaling, so we haven't done very many weak scaling studies, in part because it's a lot harder to do that with circuits and have it be the same problem.
Sure.
So if you're looking at a finite element calculation and you want to make it a bigger problem, you can just refine the mesh a little further, and it's still the same domain, right? And with circuits, you're basically adding more transistors or something. And so
using sort of synthetic generator, yeah.
Yeah, and so we can synthetically do that, but then it's not really the same problem anymore, and so then it's a little harder to do that meaningfully, and so we haven't done it as much. But I think, if it was a matrix that had a really nice structure, one that could really be exploited by some of the methods that we're using, then I think you could go quite big and see pretty decent scaling. At least that's what I believe. Most of the people in my group, we're not circuit designers, so it's hard for us to produce a meaningful, huge circuit on our own. We usually need to work with somebody who's designing them to get test cases that are that big. So that's
maybe Matt can make some with Open RAM for you.
Yeah, no, actually,
Yeah.
Memory. The fact that there's these memory compilers under development like Open RAM, I'm actually pretty excited about that because I for myself, I see that as an opportunity to produce large test cases. If I can just take the time to learn how to use it, it's
Yeah, I think our installation stuff is at this point you were a couple of years ago. So
okay, right.
So I saw
yeah, no,
Xyce is on.
Oh, go ahead.
I saw Xyce is on SPAC. Does that not make things a little bit easier for some people in some cases using SPAC
Yeah,
at all? Or
SPAC just happened really recently. The same guy that implemented the Python API also put it up on SPAC the other day. So that really just happened like last month.
oh,
What
cool.
is this?
It's
So-
HPC centric package manager.
Oh, okay.
Yeah, so yeah, if you're on, I mean, I don't think SPAC will work on Windows, but if you're on like an HPC based, Linux or something like that, it works. And so there's a SPAC recipe up there, and you can just run it. As far as I know, I haven't tried it yet. I just know that,
Yeah.
but the guy, I trust that the guy who did it knows what he's doing, and it should. I think for a lot of people that would help. So
Yeah, that's good. Yeah, it'd be interesting because I know you guys are you were working on support for the Skywater open source PDK stuff.
yeah,
And that actually had some variation models that are not really used right now. So it'd be interesting
okay.
to kind of,
Yeah.
they're in the comments still, but they're basically not.
Okay.
I don't know if they didn't put them in the public release, but they're in the NDA one and they can release them if they're not.
Okay. Yeah, I think I have access to the NDA version. I think.
Yeah.
But yeah, actually, I mean, mostly, getting Xyce to work with Skywater was mostly about just making sure that a handful of things were done a little bit differently in Xyce. The biggest one was like paths for include files. So you have a circuit that's including a library from over here that subsequently includes other files over there. I think we had hardwired it so that it all thought it was relative to the directory you were running from, and that's not necessarily the way PDKs are set up. And so now it's a little bit smarter. Now it attempts to use relative paths relative to the PDK file. So I think that was the biggest thing that was making it hard for some people to use it. But and maybe a few other little things like yeah, but I think we added a bunch of stuff for 7.3 that I think makes that easier.
Cool.
But yeah, I mean,
all right.
One thing with Spice simulators is that every version of Spice has slightly different syntax, and supporting all of them is takes actually a fair amount of effort. We actually do have a tool that we also release called XDM that allows you to translate between file formats. So it basically, at least in theory, it'll translate from PSpice to Xyce and from HSpice to Xyce and also from Spectre to Xyce. So we started with PSpice, then did HSpice. Spectre's the most recent, probably the least mature. But that tool XDM, we're actually planning to have it eventually evolve into our parser, so it'll just be part of Xyce. But right now it's a separate tool. But for somebody who's
be really useful.
Yeah, for somebody who's running an industrial circuit, that was developed in a commercial PDK, that kind of translation is crucial. So,
absolutely.
On a related note, I noticed this code was released GPL v3. Did that cause any problems with your government sponsors? Or
so far, no. I mean, essentially,
that's great to hear.
Yeah. So let's see. There's a long sort of history with that, but if anything, we've been given pressure to have a more permissive license. So to the extent that we've gotten feedback, it's been from people saying they would prefer it to be something like the MIT license or the BSD license.
Yeah, as a former LPL employee, we were pushed that way.
Well, yeah, and we've thought about it. I mean, we may still change in that direction. We just haven't done that yet. I think initially we were being a little cautious. We had a lot of circular discussions about which license should we use, and eventually we just had to choose one. So,
because the government wouldn't have to follow the GPL. Like they don't have to release whatever they want. Just like they can use your patents and not pay you. So
yeah, so if we're, I should say we have a multi-licensing model. So if we're dealing with other government labs, there's a government use license that we can set up. That's separate. And if, in theory, not that this has happened really, but in theory, we could do commercial licenses too, if we wanted to. But that could be done outside of GPL if all the stakeholders said yes. So, but yeah, mostly, mostly when we've been interacting with other groups and other, other people doing research and so on. I mean, the main feedback we've gotten is it'd be really great if you could switch to MIT or something. so that might happen. We'll see. That's another discussion.
All right. Well, I've got another meeting now. So yeah, thanks for
right.
joining us. That was a really good talk. I enjoyed it.
Well, I'm glad you enjoyed it. Thanks.
Yeah, great tool.
Thanks for having me.
Thank you.
Thank you.
All right. Bye, everyone.
Bye.